Okay, so I was talking about the gradient of the graph, and by now, I think most of you would have probably guessed what I was talking about. But for those who did not, we're going to do it right now. Okay, it was a smiley face for V. It was a smiley face for V. Yeah, it was a smiley face for V, and it was not a smiley face for E. It was something like this. Okay, this graph looks terrible. Oh, it seems that we have 10 minutes left in this meeting, but never mind. Let's continue with this first. Okay. All right, here we go. This was minus VE max, and this was plus VE max. Let's say this is point A. Let's say this is point B. And let's say this is point C. At point B, electric field is going to be 0. That's pretty obvious. This is E, this is D, this is D. And we know that we're going to have 3 different points here as well. Okay, let's say this is point B, this is point C, and this is point A. Now let's look at this comparison. And this is like the crucial part, which you have to get. When E is plus VE max, we know that the gradient is minus VE max, right? The gradient is going to be minus VE max. And when E is minus VE max, when electric field is maximum in the negative, we know that M at C is plus VE max. So while I can say that E is KQ divided by R squared, I may not be able to say that M is KQ divided by R squared. I think a more appropriate answer is minus KQ, KQ divided by R squared. Let me erase this and let me write it in a better way. So EFS, electric field strength, is minus VE, potential gradient. So M is the potential gradient. Why potential gradient? Because this is the potential graph, and we call this gradient the potential gradient. So this is the potential gradient. And by now, you have probably guessed that electric field and M have a negative relation. So we can say that E is equal to, so let me write it down here. So M is minus VE. It is the negative of E. You can say minus E as well, or minus KQ divided by R squared. So we can say minus E. They have this relation. Why? We literally just proved it. So I'm going to make the lines so this makes better sense. Let's use a red color and let's make them like this and like this. Yeah, I think that should be fine. All right. Yeah, and that's it for this part. Did this make sense? Are you guys with me? Does anyone have a confusion here? You can ask your questions. All right, I'm giving you some time to note this down. If you haven't, once you're done, tell me so we can do the next thing. Let me add up. Yeah, I know it. Thanks for reminding still. I think we're going to end the meeting right after you're done noting it down. So this can be better. So M is rise over 1. Just writing this down so all of this makes better sense. Okay, KQ divided by 5 divided by 5. And yeah, V is KQ divided by 5. All right. When you're done noting it down, just tell me. Okay, sure, Legina. Sure. So while you are noting it down, I'll give an overview. So we made these graphs for same charges. let me write it down. Both of these graphs are for same charges. So when you're memorizing, I would suggest that you memorize it like this. You know, same charges, this graph and this graph. Opposite charges, that graph and that graph. Now, the reason I made them like this, you know, next to each other, is so I could prove that m is minus e. A lot of questions will ask you about potential gradient and stuff, and when you're doing the question and you don't know this, it's going to be confusing. So here I know that this is plus VE max and this is minus VE max. I made this as point A and I marked this as point C. And the middle one is obviously E is equal to 0. That's the point B. When we make the gradients, we notice that yes, indeed at B the gradient is 0. But at A, the gradient is maximum, but it's not positive. The gradient at point A is negative, telling us that E and M have a very interesting relation, that is M is equal to minus E. And at point C, E is minus VE max, while M is not minus VE max. At point C, M is plus VE max. And that proves my point that M is equal to minus E. But conclusion of all of this is electric field strength is negative potential gradient. So remember it like this. Anyway, I hope all of this makes sense. I'll end the meeting and we're going to continue this in the next meeting. All right. See you guys in the next meeting. Okay, now let's mark the points again. Okay, this is point A. This is point B. This is point C. That's point A. That's point B. And this is point C. Now, these are two graphs for opposite charges. Let's prove that thing again because I have just shown you one example. What if this one does not work out? So both of these points are plus VE max. At both of these points, electric field is plus VE max. Okay, and at this point, at this point right here, E has a minimum value, so minimum value. And yeah, maximum again. All right, now let's show this on this graph. At point A, I know that potential is maximum, but I'm concerned about the gradient. Okay, I have a question for you guys. What is my gradient gonna be at point A? What is the gradient at point A? Is it maximum? Is it negative? Or is it positive? Come on, guys. What is my gradient at point A? Yes, it's max minus VE. Good job. It's max minus VE. So max minus VE. All right. Over here at point B, indeed, the gradient does have a negative value. It can be a bit confusing, but don't get confused because at this point, the gradient is not 0. Yes, it's not 0. The gradient at this point is minimum. It's a slanted line. We do have a gradient at this point, but it's not maximum. It's minimum, right? So at this point, M is going to be minimum. Now let's make the gradient here at the last point. So you can observe that over here, I think this is an excellent display of what is actually happening. If we want to show this, you can see that here it's max, but this line, the slope of this line, it slowly decreases, and then it finally reaches this point. And then again, it increases in the opposite direction, right? It increases in the opposite direction. Okay. So just with these two things, we have proved our point. But just for the sake of it, let's show the gradient over here. I think the gradient is going to be something like this. Right. It's going to be plus VE max. And yeah. All right. Now, over here, it can be a bit confusing, but I would like to make a correction here. This is going to be plus this part. Let's say it's for the plus charge, and this part is going to be for the negative charge. That's why here we're going to have a minus max VE, and here we have a plus max VE. That's pretty much it. Sabina, what do you mean? Is it max positive or negative on the VD graph? What do you mean? Can you please rephrase it? All right, so meanwhile, let's minimize this. Yeah, so note this down and we're going to do the next thing. Okay, when you're done noting it down, do tell me. Okay, that's great. Okay, that's amazing. All right, let's leave it at that. And let's start the next thing. Okay, the next thing we're going to do is going to be electric potential energy. All right, electric potential energy. All right, so can anyone remind me, what's the formula for V, Q, and W? There was a formula that used to relate W, Q, and V. Does anyone remember that formula? Work done and voltage and charge. Come on, guys, I think it's a really common formula. Yeah, you can say that, but we're going to write this like this, right? So W is equal to VQ, right? It's the same thing, right? And this W here, you can write it as U, right? So V is potential difference and Q is the charge moved. It's the charge moved. And W, this is the work done, or this is electric potential energy. Both of them are in joules. They're the same thing. And yeah, that's the basics of it. All right. Now we're going to make a little situation here. So pay attention. I have a charge here. This is plus 10 microcoulombs. And I have a negative charge here. This is minus 5 microcoulombs. This is plus 10 microcoulombs. And the separation between these two charges is 10 centimeters. This is going to be 10 centimeters. And we have a dotted line here. We have a point here. This is point B, right? And this is point A. And this distance, this is 5 centimeters, and this is 5 centimeters as well. Now, this is a very interesting situation, and this is a question for you guys. Now, we've done a lot of concepts. Let's do a question. Calculate the work done in moving a 5 nanocoulomb charge from A to B. You guys have 2 minutes starting now. Solve this question. So we're moving this little charge of 5 nanocoulombs from A to B, and they're asking you the work done. You have the formulas, and we've done a lot of formulas before this. You can solve it. When you guys are done solving this, do tell me in the chat so I know when to start discussing. All right, guys, this is an easy question. One last minute. I'm giving you like one last minute. Uh, if you have an answer, just send in the chat. All right, 30 seconds to go. Okay, we have one answer, and yeah. All right, what about the rest? Are you guys still solving? If you need a little bit more time, you can tell me. But if you haven't solved, I mean, that's a different scenario. Okay, Sabina has an answer. Good job. What about the rest? There's 9 students here, and we have 2 answers. All right, guys, time's up. Um, if you have an answer, please send in the chat. Okay, Ruwafa says he's solving. Okay, I'm giving you 20 seconds exactly when this meeting exactly hits 15 minutes. We're gonna start discussing. All right, 5 seconds to go, and let's do this. All right, time's up. We're gonna start discussing it. Okay. This was the question, this was the situation. Let's observe the formula. What did I mention when I was teaching you this formula? We had this formula, which was W is equal to VQ, right? And this V over here, this is not potential. It's potential difference, right? So if I want to know the potential difference in moving from A to B, it would look something like this, right? So this V, or change in V, it would be VA minus VB, right? So the first approach should have been to find the potential difference, because we know that potential is just potential at one point, and we want to find the potential difference. All right, can anyone tell me what potential did they get at A? What was your potential at A, guys? So you would have probably found it like this: V is equal to KQ divided by R. And yeah, plug in the values and you would have a potential at A. Hey guys, what's the potential at A? Was anyone able to find the potential at A? All right, one hint: you would subtract this potential and this potential, because this is positive and this is negative. So the potentials, they would get subtracted. So it would be like this. I think we would get a potential of 9 into 10 raised to the power 9 into 5 into minus 5 into 10 raised to the power minus 9 divided by 5 divided by 100. Okay, guys, what's the answer here? This is potential at A. This is potential at A due to this charge. Come on, guys. What's the answer over here? All right, thanks. So this is 900, and this is potential due to this. Now, if I want to find potential at A due to this, I would just, Legina, this is potential, right? Yeah, it's potential. How is there square on the radius? Potential is V is equal to KQ divided by R, right? So basically E is KQ divided by R squared, right? So if you made this little mistake, that's fine. Okay, now 9 into 10 raised to the power 9 into 10 into minus 9 divided by 5 divided by 100. I think the answer here would be around 1800. Yes, this is minus 9, this is minus 900, and this is 1800. Now that's the trick basically. So if you want to find V at A, you would do something like this. You would add these up, but since this is a negative charge, they would subtract. So 1800 minus 900 is going to be 900. So V at A is going to be 900. By the way, what is potential at B? Was anyone able to find this so we don't have to solve the whole thing again? What's the potential at B? Can anyone please tell me? Or do I have to solve it just the way I did here? Hey, was anyone able to find V at B? Just tell me, like, no or yes, so I would know. All right, you would do the same thing, and I think your answer would be around 900. Are you guys getting this answer? Come on, guys, are you guys getting this answer? Yes, I mean, you should have told me earlier then. So this is 900, and this is the potential at B. That's what I was asking. Okay, now you would subtract these two. This would be 900, and this would be 900. What is 900 minus 900? Come on, basic math, like too great math. 0, right? Now, plug in this value into the formula, and you would get 0 into Q. And what's the answer? 0. So the answer is simple, 0 joules. Nothing complicated. The answer is 0. You would be doing no work in moving a charge from A to B. That's just the right answer. I hope it made sense. If anyone has a confusion, you can ask me. And yeah, let's move on. Eliza, look, the charge was moved. We did move the charge from A to B, but we did no work. No work was done in moving this charge from A to B. Why? We just proved it here. What is 1800? Gina, this 1800, look, when finding the potentials at A and B, we have two charges, right? We have two charges. So this is V at A, this is V at A due to the positive charge, and this is V at A due to the negative charge. So when I subtract them, I end up with 900. You would do the same thing for B, and you would end up with 900 as well, right? Because this is 5 centimeters as well. This is 5 centimeters as well. So VB and VA turn out to be the same. And that's why you're doing no work. So whenever you have a situation where the distances are the same here and here, it turns out you do no work at all. Okay, I'm gonna give you one question and you guys are gonna solve it by tomorrow. So note it down and yeah, we're gonna continue all of this tomorrow. So the question I'm gonna give you is this. We have a positive charge here, then we have a negative charge here, and we have a point A, and we have a point B. The distance here is going to be 20 centimeters. This is going to be 5 centimeters. This is 5 centimeters as well. And this is plus 10 microcoulombs. And this is going to be minus 5 microcoulombs. And you have to find again the same thing. Work done in moving a 5 NC charge from A to B. All right, so note this down, and yeah, that's your question for tomorrow. By the way, I want to ask you guys, how many of you guys in this class have studied A2 before? And how many of you have never studied this before? Like, how many of you are doing this for the first time? And how many of you are doing this? Okay, Legina says she's doing it for the first time. That's great. All right, that's cool. So a lot of you have not studied it before. That's great. Okay, so the reason I asked this because I wanted to ask you about which topics would you want to do first. But since you have not studied this before, I guess we're just going to go with the flow. Is anyone planning to give October and November exams for A2? Or all of you are focusing on May, June? Okay, Sabina, you are giving it an A2. That's great. That's actually amazing. Yeah, so for the ones who are giving it in May, June, I think you guys are going to do great because your concepts are going to be clear by the end of summer. And I guess your study sessions will take you to, yeah, the completion and the past papers, and you're going to be well prepared. Anyway, that's good to hear. I hope you guys have noted this down. I am about to end the meeting. Are you guys done noting down the question? Is there anyone who is still not done with noting it down? Okay, that's great. Anyway, have a nice day. I'm going to answer that tomorrow. Anyway, see you all tomorrow. Have a nice day. Tomorrow, we're going to finish this chapter and we're going to do some questions from the past papers. See you tomorrow. Allah Hafiz. Bye-bye.